this video we'll be going over synthetic division. Synthetic division essentially simplifies the process of polynomial division whenever we have a polynomial divided by a linear binomial. And there's a few conditions here. So the first one is that we're dividing by a linear binomial, meaning that we have the binomial has a degree of 1. We also want the binomial to have a leading coefficient of 1. The x term only has a coefficient of 1. Now, it is possible to do it with coefficients of 2 or 3 or whatever coefficient you want, but you'll have to do some extra stuff and it might get more confusing. So we'll start with just a leading coefficient of 1 for the binomial. So I have the initial setup here, and we have basically in synthetic division, we just want to write the coefficients of the polynomial to the right of this kind of upside down version of what we have here. Now, what else do we need to set up this? Well, the other thing we need is to incorporate the linear binomial. So in order to incorporate the linear binomial, we write that in the same position as it would be over here. We write that over here. Now, what do we write over there? Well, we write whatever is the opposite of this one. So just remember that it's the opposite. That's one of the key points to remember. So essentially, since this is x minus 1, we're going to put a positive 1 over here. So that's just one of the most important points to remember. So now, let's first start off with what we normally do in this long division process. So the first thing that we usually like to do is we put an x squared term to match up the degree and the coefficient. So in order to match up the degree and the coefficient, we multiply the x squared times the x, which results in an x cubed. And then we multiply the x squared times the negative 1, which results in negative x squared. Negative x squared. We now then subtract the entire thing, and then we see that this results in the two terms x cubed and x cubed cancel out because there's a negative distributes, and then of course we're left with 2x squared plus x squared because the minus distributes, and that leaves us with 3x squared. Now, maybe the person who invented synthetic division was like, hey, we're using negatives over here, but it's kind of redundant because this is going to be negative anyway. Because we see that, well, when we multiply the x squared times the negative 1, it's negative anyway. So why don't we just make this positive? And maybe that's why he took this opposite over here. But since we did take this opposite over here, our process is also going to be kind of reversed. Because instead of doing the subtraction we do here, it makes sense that we would add instead because we took the opposite of here, so we might as well take the opposite of the operations. And we'll see why that pattern makes sense. So the first key here is that the part under this over here is going to be the quotient, or what will be over here. So essentially, we just drop down this first one, and it goes directly down like that. Now, why do we do that? Well, it makes sense because whatever coefficient is over here, is on this x cubed term, will always be the coefficient of the first term of the quotient. Now, why is this? It's because we explicitly said the condition that the leading coefficient of the linear binomial is going to be 1. Take this example, for example. So let's look over here. So we see that there's a leading coefficient of 2. Now, we see that there's a coefficient of 1 here because that was the condition that we wanted. So in order to match up the coefficient and the degree, most importantly the coefficient as we're referring to here, it's going to be the same as the coefficient of the largest degree over here. It's going to be 2. Of course, 2x squared. So on that idea, we already know that the leading coefficient of our quotient is going to be the same as the leading coefficient of this polynomial. So we can directly drop down the 1 over here. Now what do we do next? Of course, we see that once we got this term over here, we not only need to multiply it to the x squared times x, but we also need to multiply it to the x squared times negative 1. Now the reason why you don't really see the x squared times x anywhere in this process is because he noticed, the guy who invented this noticed that, hey, why did the x cubed and negative x cubed always cancel out? Well, that's because we made it like that. We match up the coefficient and the degree so that it cancels out. So that's why we don't even need to consider this step over here, x squared times x, because it always cancels out anyway. So then he's like, okay, so how do we do x squared times negative 1? Well, since x squared times negative 1 is going to be negative x squared, and we're going to subtract it anyway, then that's similar to, let's multiply our quotient. So multiply our quotient to what's over here. That's like multiplying this x squared to what's over here. And since subtracting a negative is the same thing as adding, but we already accounted for the negative over there, we made this positive. Since subtracting a negative is the same thing as adding, we're just going to multiply this 1 times 1. And we're going to put that and add it to 2. And this should make perfect sense. And I'll actually do that in a different color. So this should make perfect sense because when we're subtracting a negative, we're essentially adding the 2 plus the 1 because the negatives canceled out. And that's exactly why when we add 2 plus 1, we see a 3 over here and we see a 3x squared over here. Now, why did we drop down the 3 immediately to our quotient? Because we already know, again, that x, since it has a leading coefficient of 1, we already know that we're going to be dropping a 3 over here. A 3 over here. And since we want to match up the degree as well, we're going to do an x term. So now it should start to make sense what we're doing. The reason why we're able to drop it down immediately is simply because we have a leading coefficient of 1 on this linear binomial. So that is the very important part of this. Now let's move on to the next step, and it works very similarly. So let's first do the normal long division. So we're going to bring down the number of terms. So that would be 3x squared minus x. Now we multiplied. We already know that we're going to multiply by 3x. And we know that we have a 3x squared over here because the coefficient and the degree is going to match up. Then we multiply 3x times negative 1 and we get minus 3x. We then subtract everything. And we are left with negative x plus 3x, which results in 2x. Let's see how that correlates over here. Since we're not accounting this first step, the 3x times the x, since we know it already cancels, 3x squared minus 3x already cancels, we know that all we have to account for is now this negative x plus 3x. Now since we're doing the addition process here, instead we're going to multiply this 3 with whatever this is over here, similarly to multiplying our 3x times the negative 1 and then subtracting it. We're going to multiply the 3 times the 1 and add it. So let's do that. So we know that 3 times 1 is simply 3, so we put a 3 over there. We know that then negative 1 plus 3, because we're doing addition here instead of subtraction, negative 1 plus 3 is equal to 2. And now, instead of continuing this process, actually, let's just continue it just to finalize things. So let's drop down the negative 2. Drop down the negative 2. And we see that when we multiply by 2, because we already know that we're going to drop down this term over here, when we multiply by 2, we see that 2 times x will result in 2x. 2 times negative 1 will result in negative 2. And then when we subtract it, of course, we'll be left with 0 because both the 2x and negative 2x cancel out with the negative 2 and 2. So let's see how that holds up here. So we see that 2 times 1 using our process, multiplying this number times this number. And we're doing 2 times 1, and then we're writing that over here. So 2 times 1. And then we're adding, so we get 2, negative 2, plus 2, and that will result in a 0. And I made this green because this is important. This is the remainder. This 0 is the remainder. So let me write that. Remainder. That 0 is the remainder of whatever we're dividing by. So now how do we turn this into the full solution? Well, you may have noticed that this 1 matches up exactly with this coefficient. This 3 matches exactly up with the coefficient in the long division. And the 2 matches exactly with the constant term. So how do we finally write this? Well, what we do is, since we know that we're dividing a degree 3 polynomial by a degree 1 polynomial, or linear binomial, we know that that's going to result in a degree 2 polynomial. So we know that this is going to be of degree 2, this 1. So you write x squared. And we know that we're just moving down from that. So we're going to go plus 3x plus 2. And there's a remainder of 0. So this is our final answer. This is our final answer. And as you can see, this process uses much less extra letters or characters over here. And it's much easier to appreciate than our process of long division over here. So now let's move on to a different example that showcases something new. So we'll move on to this example. Now, you may have noticed something different here, and this time there's a 2x cubed, as I briefly mentioned before. So first, before we do any of that, let's set up the process. So first, over here, we write down the coefficients of whatever polynomial we have, and that would be 2. This coefficient would be 1. This coefficient would be 3, the x coefficient. And this coefficient would be 10. Now, let's write down the opposite of whatever's over here. So the opposite of whatever's over here, and that would be positive 5 instead of negative 5. So positive 5 instead of negative 5. Now, let's look at what happens. So let's divide this normally by matching up the degree and the coefficient. So we know that to match up the coefficient, we need to have a 2, which is similar to dropping down this 2 over here. So our idea from before still holds. We're going to drop this, the first one, directly down. We know that then to match up the degree here, we have a 2x squared. And you see that over here, we don't need to do that because we have eliminated that part of the process. Then 2x squared times x will be 2x cubed, as we wanted. 2x squared times negative 5 will be negative 10x squared, as we also wanted. And then we'll subtract this. Then we'll subtract this, and we see that the 2x cubed minus 2x cubed will cancel out. And then we have x squared plus 10x squared, and that'll result in 11x squared. So now, since it results in 11x squared, let's see what happens if we do the same process. We do the same process that we did up here. Let's see how that holds when we do that process with this. So what we did is we multiplied. The first thing we did is that we multiplied this to this. So let's do that. 2 times 5. 2 times 5 is going to be 10. So then we write down the 10 over here. We then do 1 plus 10, because we're doing addition, not subtraction, which is one of the key things to remember. And now we got 11. just like we got over here. So now, the thing is, instead of continuing this long division over here, let's see how much easier this will be if we just do synthetic division from now. So let's continue. We multiply this over here times this over here, this 5, 11 times 5, and that'll give us 55. So 11 times 5 will give us 55. We then do 3 plus 55. 3 plus 55 gives 58. We then do 58 times 5. So 50 times 5 is 250, plus 8 times 5 is 40. So 250 plus 40 is 290. So 290 we write down over here. And we know that 290 plus 10, and I'll do that in a different color because we know the last one's going to be the remainder. 290 plus 10 is 300. And as you can see, we didn't have to write any x cubed or x squared or subtractions or cancellings. It was so much simpler to visualize the synthetic division. So now let's write this in as a final answer. So we know that we divided a third degree polynomial, or an x cubed, by an x. So we're going to result in an x squared. So our first one is 2x squared. And we can just go continue from there. So that becomes 11x. Then we get plus 58. And now, since we have an extra 300 over here, as we saw in the previous video, we're going to write that in a special form as 300 over what we divided by, what we divided by. So that was 300 over x minus 5. And that will be our final answer. So now, since we have that, let's move on to the final problem. And I highly encourage you, just try the long division out and see if you get the same answer. And you'll realize perhaps how much quicker this version would have been. And maybe less tedious as well. Let's move on to the final problem and this time I won't even write down the long division part of it. So first, as we know, we're going to copy down the coefficients of the polynomial. But here we do have to be careful. The reason why I selected this example is because we notice that we have 3x to the 4th, 2x cubed, and then minus 16x. Where did the x squared term go? Well, that'll actually be an important part of what we're going to do here. So in long division, we'd seemingly just add a space for that term. But over here, we also have to add a space for that term. So it's very similar to what we do in long division if we encounter that case. So we write down the coefficients, which would be 3. Then we write down 2. But of course, we have a 0x squared, so we're going to write down a 0. We then have minus 16. And finally, 14. Now let's continue with our normal process. We select the opposite of whatever is over here, and that'll be negative 4. So I'm going to write down negative 4, and that's also something different. This example is very instructive. So we drop down the 3, because we know that it's going to match. Then we have 3 times negative 4 is negative 12. We then add 2 plus negative 12 will be negative 10. Then we do negative 10 times negative 4, which will be 40. Then we do 0 plus 40, which will be 40. We then do 40 times negative 4, which will be negative 160. We then do negative 16 plus negative 160, which will be negative 176. And now for the finale, we have negative 176 times negative 4. So 176 times 4. So we can split that up. We have 100 times 4 is 400. 70 times 4 is 280. So far we have 400 plus 280, which is 680. We then have 680 plus 6 times 4, which is our last one, and that results in 704. And I'm going to write that in a different color because it's a remainder. So you can verify that works. We know that the negatives will cancel out as well. So it'll become 14 plus 704 which results in 718. And we can see how much quicker that is than our normal polynomial long division process. It's clearly a much more efficient way. So there's a few things I want you to notice here. We noticed that we have a 0. We had to add an extra 0 over here, and you would have to do that likewise in the long division process, unless you can somehow fit it into that space in the middle. We also know that we have to have the opposite of this term, even if this is positive. In the previous examples, we had that being negative, but this time we have it being positive. So we had to keep the opposite of that over here, which was negative. So now let's just in fact write down what our final answer was. So we know that we're dividing an x to the fourth polynomial, or fourth degree polynomial, by an x by a first degree polynomial. So that will result in an x cubed. So we have 3x cubed as our first one, and then we can move from there. So then minus 10x squared plus 40x minus 176, and finally plus the remainder, which will be 718 over x plus 4. So how do we summarize what's going on here? There's a few things you have to remember. So you have to remember the opposite of this term. We want the opposite of whatever we have over here. So plus 4 would be negative 4. We also need to keep in mind that we have to add an extra 0 if we skipped any terms. We also have to keep in mind that this process, it resembles kind of like an alternating mountain pattern, maybe something like that, and then maybe that'll help you visualize it better. And it's essentially the same as what we're doing in the long division process. So if you ever forget, just remember that, okay, well, since we know we have to drop down the first one, since it's always going to be that way, because we have a leading coefficient of 1 for the linear binomial. Then we're multiplying it to this part, which is similar to how we would multiply the quotient, the first term of the quotient, to the 4 and subtract it here. And we know that we're not subtracting here, we're adding here because it makes things easier, perhaps for less computational mistakes. And so that is what I have to summarize about synthetic division. Now, I encourage you to research more about synthetic division and why it's useful. And we'll see that it's very useful because in the first problem, you may have noticed that the remainder is 0. So I'd like you to think about what that means. What is the relationship between x minus 1 and x cubed plus 2x squared minus x minus 2? What is the relationship between these two that does not happen when we had a remainder like in the last two problems? So I hope you enjoyed this video.